And the next speaker is Borja Raquena Pozo from ICFO, Institute of Photonic Sciences in Barcelona, where he is a PhD student in group of Maciej Lewenstein. Yes, please.
Hi.
The stage is yours.
Sure. Okay, well, I can start while this goes on. So today I'll talk about a project that I've developed with Gorka and Maciej, who you may know are here. And then Vedran and Jordi from Leiden. You'll get to know Vedran next week, actually. And in this project, we combine relaxation methods with reinforcement learning. Now, you're a bit familiar with reinforcement learning. I'm aware most of you will not be much familiar with relaxation methods. So don't panic, I'll try to give a nice introduction into this. And well, my main goal is that you don't get bored. And then if you also get to kind of understand a little bit what I'm doing, it's a great success.
Continue.
Right. So as you may know, in quantum physics, we often have to deal with the exponential scaling of the Hilbert space. And in quantum many-body physics, this often incurs into computational intractable tasks, which means that we have to rely on approximate methods to tackle them. And actually, in last years, some of these methods have been enhanced with the help of machine learning, such as the neural network quantum states in variational Monte Carlo, for instance. So I will illustrate the process in a very simple example that I believe everyone can understand here, that is finding the ground state energy of a many-body Hamiltonian. So in this case, well, you know, it's kind of hard. So one of the most common techniques are variational methods, which result into an upper bound to the exact solution. The main problem, though, is that whenever we have a solution, we have no way to know how far we are or what is the error that we're making. On the other hand, relaxation methods come in, and they come from the opposite direction. And so if we combine both, we can find a confidence interval with which we can assess the quality of our approximation and decide whether we want to invest more computational power or it's already good enough for us. So now, as I mentioned, we're giving some love to relaxation techniques, and I'll illustrate this with a very simple example. So in relaxation techniques, we're trying to take a very difficult problem and make it a little bit easier to solve. So I'm sure everyone is familiar with these kind of puzzles in which we have tiles and there's a hole, and then we have to move these tiles to end up with a picture. Now, in the original problem is subject to the constraints that we cannot stack our tiles on top of each other. So in this case, we would only have two possible moves. However, a very simple relaxation would be to remove or relax this constraint and allow the tiles to be stacked up on top of each other. So in this case, we would be able to pretty much move every single piece that we wanted. And this way, it would be much easier to reconstruct Jordi, which is the mastermind behind this project. And so in this case, we are lucky and we reach the same solution, but it could be that the solution that we reach is not possible to obtain given the original constraints. And hence, that's when we have our lower bound to the exact solution. Furthermore, this relaxation can be tuned in a sense that we can allow for stacking only one tile on top of each other, two tiles, or an indefinite number of tiles. And this would make the problem much easier according to the degree of relaxation. So how do we build a relaxation for our original problem of finding the ground state energy? So basically, we can write the problem as a minimization over all possible states. This is the only math we'll be seeing today, by the way. And in the first part of the equality. I don't know if you can, nice, here, right? And then a way to relax this or to make this problem simpler is to take a set of independent minimizations over reduced virtual states that span regions of the Hamiltonian. Now, I know this may sound a bit abstract, so let me give you an example. So imagine we have a system and we described it by a state rho. Now, if we wanted to perform the minimization here, we'd have to account for all the parameters of rho or all the entries of rho. However, if we instead we split the system in half and we consider these two reduced virtual states, our minimizations become exponentially simpler. As you may imagine, the farther that we reduce the size of these chunks, the easier it is to solve the problem, but then the rougher the estimation that we have of the actual solution. Furthermore, well, we allow these regions to overlap, and these control the constraints of our problem that then we solve with semi-definite programming. But well, this is not very important now. So generally, we have limited computational resources, and so we have to find a compromise between the cost we can incur and the quality of the solution that we want to obtain. So it is very important in many applications that given a limited computational cost, we find what is the best approximation that we can obtain. And here comes reinforcement learning, because figuring out what is the best partition of our system in these terms is a combinatorial problem with many possibilities. And reinforcement learning has been shown to work really well in these kind of situations. So now I have to thank Everett for his nice presentation yesterday, because I can introduce reinforcement learning in a much lighter way. So remember, the basic blocks in reinforcement learning are an agent that interacts with an environment. And so this agent observes a state of the environment and can decide to perform a certain action. This action modifies the state of the environment, or maybe not, and then the agent receives or observes the new state at which it's in, and together with a reward signal. And the objective of the agent is to maximize this reward. And this is how we guide our agent towards our solution. In this case, the actions would be our current distribution of reduced virtual states. Then the agent, with these actions, can propose a new distribution, a modification to the current one. And so the new state is basically the result of performing this modification. And then the agent receives a reward that we obtain through semi-definite programming that depends on both the quality of our approximation to the optimal solution and the computational cost that it's taken. So, and the way that we have to limit the overall computational cost is by limiting the size of the reduced virtual states. Now, there's a question over there.
How do you measure the quality of approximation when you do this, when you give the signal back to the agent?
Yeah, so since we're obtaining always a lower bound, we just basically, the higher it is, the better. It's pretty simple in that sense. I mean, we have a reward function that is more complicated, but I don't think it's worth diving on it right now. If you want, we can discuss it later on, but it's basically the higher, the better. Right. So we apply this framework into the.
Sorry, Borja.
Oh.
Here.
Nice.
I have a question, and I just thought maybe it's fitting to ask it right now, because why do you know that you always have like a lower bound? Like, where does it come from that you always know that you're beyond the true energy?
I mean, this is just by construction of the algorithm. The same way that with variational methods, you're always obtaining an upper bound. By construction of relaxation methods, you have a lower bound. Considering this is a minimization problem, if it was a maximization, it would be the opposite way, basically, for both methods.
Oh.
Actually, it's not always a lower bound. We can also have the exact solution if we're lucky enough.
Okay, but this just comes from like basically that you're just splitting this into these different.
Yeah.
Okay. Okay, thank you.
following the same question. So if I understood correctly, you can have a relaxation. You can construct your relaxation in such a way that you don't have a lower bound. So you need really to be careful that your relaxation is well posed in a sense. That's what you meant.
Yeah. Okay. Honestly, for any system of interest, you'll probably always get a lower bound. Like, for instance, well, you'll see then when I show the application on the XX model, when for example, the ground state is a product state, it can be described by the one body marginals, basically. And so you can, with any relaxation that is equal or more complex than that, you obtain the exact energy. However, when we start having entanglement and so on, we would need the entire density matrix to describe it. So doing this kind of partitions lowers the energy that we have. I don't know if that solves your...
And that's something you can prove analytically, right?
Yeah.
Okay, thanks.
Well, I can't, but very smart people can. Right. So we've applied this framework to finding the ground state energy of the XX Heisenberg model. And well, I'm not an expert on this model, but the most important things that you need to know is that written in this way, there's a phase transition at B over J equals 2, above which the ground state is a product state and below which the ground state is entangled. And so here comes the first interesting results that in the...
Right, so
The reason why you have a phase transition in a finite size system is that there is conservation laws, and simply this is the crossing of the levels. Different states become ground states. That's why there is phase transition in a finite size system. Remember.
All right, so here what we see is a depiction of a system of 6 spins, which are the darkish balls, and they are connected. It's a periodic 1D system. And then in colors, this would be like a representation of our reduced virtual states and the region they span. So here what we see is that basically our reduced virtual states span 2 spin each. It should be 1 spin, but this is due to some implementation details. The interesting part is that within the entangled phase, we, instead of finding one solution, we find 3 different solutions. And then what we would expect is that this result over here, this is like the highest and most complex relaxation we let this agent to build. But in some region of the phase space, this other one here that is made of smaller chunks, as you may see, actually provides the same or even better approximation to the energy. And this is not obvious at all. Then we apply transfer learning to this approach, and we try to explore the phase space of our system. So in order to do so, we train an agent deep into one phase, so at B over J equal 5, and then we use this pre-trained agent to solve the same problem in other points. There's a question. What do colors indicate? Nothing. It's just to be able to distinguish the different virtual states. The colors don't have any meaning. It's just to see them better. Right. And so we take this pre-trained agent that we train deep into one phase, and we use it as a starting point to solve the same problem across the phase diagram. And then we compare the time it takes between finding the optimal solution with experience and training from scratch. And so if we have a ratio that is lower than 1, it means that we have a convergent advantage. And this is what we see in this plot. So in this plot, during the unentangled phase, we have like significant advantage, mainly. Oh, yeah.
Hi, thanks. Sorry, can you now it was a little bit too fast for me. Can you go step back? So now this sounds very fancy with the transfer learning. So you basically just train at the 0.5 and then you validate at another points, or you like take the pre-trained model and keep retraining, or how exactly, what do you mean by transfer learning?
So we train the model here, and then we use it as starting point to retrain it in a different point in the phase diagram.
So you really initialize the weight, but continue training. Okay.
Exactly.
Okay. Perfect. Thanks.
Right. And so what we see is that in the unentangled phase, there's a massive advantage, mainly because the optimal relaxation is the same across the entire phase. But then we see that as we go to the opposite phase, the advantage diminishes quite sharply. And as we go farther and farther, it diminishes even more until here it's even a little bit worse than what. So with this, in an autonomous way, we can explore our phase diagram, and actually this method hints changes in the ground state of our Hamiltonian, some of which may be due to phase transitions. Then, since yesterday there was some discussion regarding why to choose reinforcement learning and so on, we compared reinforcement learning with other methods, such as breadth first search, which is the green line, and Monte Carlo optimization, which is the orange line, and perform this optimization for different system sizes. And so as we have larger systems, the exploration space increases quite fast. And so we see that the reinforcement learning approach outscales the Monte Carlo approach. And actually then we tried with even larger spaces, and we see that it outscales it much sooner. So in this case, the overhead of learning compensates for large systems because the agent is able to explore the space more efficiently, exploiting the knowledge that it's accumulated during the initial steps. Finally, to conclude, we've developed a framework to optimize relaxation methods, with which, by the way, we're using reinforcement learning, but we could, as I show, we could use any other optimizer. We just found it works better. And then we can use transfer learning to explore the phase diagram of a system in a very autonomous way. And then the method can be, so I illustrated it with finding the ground state energy of a Hamiltonian, but it can be generalized to any other optimization process that we can pose as a semi-definite program, as it is right now, such as for building entanglement witnesses, or doing sum of squares representations, or whatever thing we may come up with. So thank you very much, and I hope you understood something.
Thank you very much for the great talk. And now we have still lots of time for questions.
Yeah, thanks. I still don't understand the motivation of the work. So you said that when you minimize, when you try to compute the ground state variationally, you don't have control on the approximation, but I guess this is not always true. Like sometimes you can really know how far you are, and then you just keep minimizing until, I don't know, you reach a plateau or something. So in this sense, the motivation was not clear to me. Like, what is this confidence interval that you talked about?
Yeah, so
at the beginning.
Yeah, so actually, when you're using variational methods, unless you can solve the system beforehand, which then is kind of pointless, you really can't have an idea of what is this distance. Like, yes, you can, like your algorithm may have converged, but it's not necessarily the global optimum. Like maybe even your variational method is not able to represent the exact solution, or it may be orthogonal to it. So you're bound to never find it. And you don't know this beforehand, sometimes. And so even if you actually found the exact solution, you need additional methods to actually prove it. You cannot tell just from the variational method result. Like maybe Monte Carlo or tensor networks approaches, or whatever other methods.
Okay, my second question, how would you do this in an infinite dimensional setting? Like assume you're solving the Schrödinger equation for molecules, for example, and then your Hilbert space is L2. How would you partition? Like what's partitioning in this setting?
Honestly, we haven't thought about this yet. So so far we've started with spin systems. So, well, I don't know, maybe Gorka has an idea, but.
Okay, thanks.
Can you
I have,
come?
sorry. Okay, I'll ask later. I'll ask in the break. Thanks.
Can you come back to the slides with the colors, the circled colors?
Yeah.
Oops.
Getting there.
Yeah. So in the entangled ground state phase, your reinforcement learning.
Hold on, who's talking?
Yeah, yeah.
Oh, nice.
Sorry. So in the entangled ground state phase,
Yeah.
the reinforcement learning algorithm still finds, let's say, clusters of local partitions. It seems like it's still kind of local.
Yeah. All right. Maybe I skipped through too fast through this slide. So basically here, I said we limit the computational cost by allowing a maximum size of these virtual states. And in this case, it was 3. That's why in the leftmost, you see like this kind of bananas of 3 spins, basically. And so, yeah.
And so have you, because there are methods like cluster, Gutzwiller ansatz, I don't know if you know this, so you separate your density matrix into local clusters. Have you compared this approach to your work or?
No, I'm not familiar with this approach. Actually, we have compared with other methods to find lower bounds to Hamiltonians that rely on similar approximations. Like, hold on a sec. So here, basically, this is called the triangular inequality. And here we're not considering, I mean, I didn't want to dive too much in the math, but here we're just taking independent minimizations. However, when we do this minimization, we impose certain compatibility between the virtual states in their overlapping regions, in the sense that we ask that they yield the same reduced density matrices. So here, for instance, in this spin, we ask the virtual state that spans the 4, 5, and 0 spins, and the virtual state that span the 0, 1, and 2, that when we trace out the complementary systems for 0, they yield the same result. So overlapping, we control what is the degree of relaxation that we provide. And then some methods, like the most basic thing, is without considering these constraints. And we have some benchmarks against these methods here. So the blue line is the Anderson bound, which is without considering this overlapping. And then the previous state of the art was a translationally invariant method that assumes certain symmetries of the reduced density matrices. And then, well, basically, here we compare with different overlapping regions. So one body overlap is what we saw. Then we can overlap 2 spins or 3 spins, depending on the size of our clusters. And with this, we can control the quality. And here, for instance, is what we see. The trivial, what we would call a trivial relaxation, that is without any compatibility constraint, yields a lower result than the others. And then exploiting symmetries is contained like within 2 degrees of overlapping. So we've also developed a generic framework that contains previous frameworks as special cases, basically.
Okay, thanks. But so, yeah, your partitions are always local in some sense.
Yes.
Okay.
Yeah. And we've also developed this for local Hamiltonians.
Okay,
so,
sure. Thanks.
The whole philosophy here is to, so to say, completely change the thing and do these relaxations in order to get lower bounds.
I have a question. So this might be a little silly, but I just wanted to check that you actually specify the relaxation problem and then you use reinforcement learning to solve it, right? You don't use reinforcement learning to find like the nicest relaxation method that could work for your problem.
No. So with reinforcement learning, we find the optimal relaxation. So the problem is the same. For instance, finding the ground state energy of the Hamiltonian, and then we can build a whole set of relaxations for this same problem. Like I was mentioning with the tiles, we can allow 1 tile stacking, 2 tiles, 3 tiles, or none, right? So the reinforcement learning part comes on figuring out what is the optimal amount of tiles that we may allow to stack. But in the end, the puzzle is solved. The problem is solving the puzzle, basically.
Right, because then I actually have like a question similar to Yahya, because then it's super interesting if you can do it for infinite dimensional systems. Because, for instance, if you can convexify a non-convex problem well and find this minima, then it's like excellent for like gradient update algorithms. You know?
Yeah.
Like, you see what I mean?
Actually, okay. So in general, these relaxations are built to provide our optimization set with properties such as convexity, so that we can find the solution efficiently.
Okay. Are you aware of any like applications of this method to like continuous systems or?
Not really.
Okay. Thanks.
Hi, I just wanted to ask, what algorithm did you use for reinforcement learning? Like, did you use deep
Right.
Q learning?
Yeah. So we did deep double Q learning with an epsilon greedy policy. I don't know if you're familiar with this.
Yeah.
Okay.
So I guess so what the partition that you do, it's actually tracing out the original density matrix into like different spins and then doing the tensor product. Are these like the states of?
Okay, I can show you. So
Okay.
this is the SDP, the semi-definite program that we're solving, and our objective function is to minimize the well, this would be like trace of rho for each virtual state, right? So basically, this is our cost function, that is the energy, already taking into account this sum. And then we impose constraints such as that any quantum state would fulfill, such as that these rows are semi-definite positive and that their trace is 1. And then the key idea here is that we ask that on their overlapping regions, maybe this notation is not the most direct to understand it, but basically we ask this thing that their partial traces in the overlapping regions match.
Okay.
Right. And
Okay.
then, for instance, if we were to solve the problem exactly, we would just like row entirely. But then if we split it into several systems that are, say, if you have a system of n spins and you take partitions of n-1, if you overlap all of them, you will have a very accurate approximation.
Okay. Okay. Thank you very much.
So I have one last question. When do you add constraints and when do you remove constraints? So can you have like some general, I don't know, settings of?
Yeah.
If you have, so just like to clarify, it's always, it's kind of general knowledge in machine learning that when you add more constraints pre-information, it's like an inductive bias, and then optimization is easier. So adding constraints is not a bad idea. Neither is removing constraints, but as you're saying, so
yeah,
if you have a certain problem, like how would you choose whether to do the one or the other?
What do you mean with this last bit?
If you have a certain problem, like you have a certain quantum system,
yeah,
and you need to find the ground state energy, which one would you choose? Like based on what criteria would you choose to do?
Okay, this is a very nice question because this is precisely what we're trying to solve here. Like we don't know a priori what is the best relaxation we can do, and in many applications, it's just whatever the person who's solving the problem feels like or can afford to do. And in this case, the reinforcement learning takes the wheel on this sense, and it decides whether to add more constraints or remove these constraints. And the way that we add more constraints is in 2 ways. One, making these partitions larger, and second, overlapping them. Then the smaller these are and the smaller are the overlapping regions, the more relaxed is the problem. So in theory, the worse the approximation that we will get.
Thanks.
Okay, so we have time for the last very short question. It can be 2 questions.
Okay. So first of all, like, wow, I love this. But
Thank
so
you.
I will ask like more like forward-looking questions, like do variational people like know about these ideas? Like, could you come up with like some hybrid thing that you do variational from above, then you switch to this, and like you know what I mean, right? What you said in
Yeah.
your motivation, like kind of really narrow down on the ground state energy for like some really, really difficult models where the variational methods alone, like as you said, we just don't know.
I don't know. Probably they are aware, but also sometimes these techniques are very common in one field and then barely used in other fields. Like this technique is widely used in quantum information,
Exactly. Yeah.
but then for condensed matter is not so used. No?
Yeah,
So
but-
this is, for instance, what we're illustrating here.
Yeah, but then your talk Then your talk tells me that it should be so. But how is your limitation with the system size scaling? Because you went up to 16 spins, and like when I do VMC, I could go much more. Like
Yeah. Okay. So okay. One thing is building the relaxation or trying to figure out what is, I would say, the pattern of these circles. And the other thing is then solving the semi-definite program that comes afterwards, that is performing the minimization. So what we found is also a very interesting result is that if we can have imagine we have a system and then we can find a reduced version of this system that has the same symmetries or properties as the previous one, the optimal relaxation that we find, so just like this pattern, for instance, if we then reproduce it in the larger one, it is very likely that it is optimal also there. So actually, I have a plot here. So on the left, we're finding what is the optimal relaxation for a system of 6 pins. And then we found that it's the same for a system of 36 pins. And then, well, in the paper, we show the same for 12, 24, and so on. So this also comes in pretty handy because we can, if we have a large system, we can find a reduced version of this system, figure out what is the smartest way to relax it, and then apply this to the large system. So this also is very helpful in finding what is the optimal relaxation because we have to solve several SDPs in the way.
And then a super quick final thing. So now your energy bound per spin, that's your upper bound on the difference between the actual energy and the energy you found. Yes? Or
no. Okay. So the upper bound per spin is just what energy we're getting per spin.
So it's just so maybe my question is this, like, what kind of precision are you getting here, right? Because you again know like how like that other techniques go to the 10 to the -5. So what is approximate?
So the precision, okay, so maybe these plots are not the best because we're taking very simple relaxations to illustrate the process. Like we let the system take up to partitions of 3 spins. But then you can ideally get up to the exact solution if your partitions are large enough. So it really depends on how much computational cost you can afford, basically.
Okay, I see. Very cool. Thank you.
Yes, so I think, unfortunately, we have to stop this lovely discussion, which can be continued later. And now we will have next speaker, Caterini Grazze, PhD student from ICFO. Okay. In the meantime, we can once more thank Borja for the great presentation.